Chapter 10. Open Channel Flow, Free Surface Flow, Specific Energy, Uniform Flow, and Hydraulic Control. Open channel flow differs from pipe flow because the liquid has a free surface exposed to the atmosphere. Rivers, canals, drainage channels, spillways, gutters, culverts flowing partly full, and irrigation channels all belong to this category. The pressure at the free surface is usually atmospheric, and the flow depth is not fixed by a rigid upper wall. Instead, depth becomes part of the solution. Gravity, channel slope, roughness, inertia, and downstream or upstream controls determine how the water surface adjusts. Because a free surface can support waves, open channel flow is strongly influenced by the relationship between flow speed and wave speed. If disturbances can travel upstream, the flow is subcritical. In that state, downstream conditions can influence upstream depths, and the flow is relatively deep and slow. If disturbances are swept downstream and cannot move upstream, the flow is supercritical. In that state, the flow is relatively shallow and fast, and upstream conditions dominate. Critical flow marks the dividing condition between these behaviors. The Froude number expresses this comparison between flow speed and gravity wave speed. Specific energy is a central idea for understanding depth changes. It combines the depth of the flow with the kinetic contribution associated with motion, measured relative to the channel bottom. For a given flow rate in a given channel, a high-depth slow state and a low-depth fast state can sometimes have the same specific energy. The minimum point between those states corresponds to critical flow. This framework explains why water changes depth over channel transitions, why choking can occur, and why controls such as weirs and gates are so useful. Uniform flow occurs when the depth remains constant along the channel. In that condition, the downslope component of weight balances boundary resistance. The Manning relationship is a practical empirical tool for uniform open channel flow. It relates flow rate to channel area, hydraulic radius, slope, and roughness. The roughness coefficient represents the resistance of the channel boundary and must be chosen with judgment. A hydraulic jump converts a supercritical shallow flow into a subcritical deeper flow, dissipating a large amount of energy and turbulence in mixing. Hydraulic jumps are used deliberately for energy dissipation downstream of spillways and gates. Weirs and gates are hydraulic controls. A sharp-crested weir raises the water and creates a controlled overflow, often passing through or near critical conditions. An underflow gate accelerates water beneath an opening and can create supercritical flow downstream. Chapter 10 teaches that free surface flow is governed not only by conservation of mass, momentum, and energy, but also by the ability of the surface to carry waves. Depth is a dynamic variable. The direction of influence depends on the flow regime. Energy can be conserved through smooth transitions, but lost strongly through jumps. Open channel flow therefore requires its own intuition, even while it rests on the same mechanical foundations as the rest of fluid mechanics. Chapter 11. Compressible flow, ideal gases, Mach number, isentropic flow, Fanno flow, Rayleigh flow, and shocks. Compressible flow becomes important when density changes are large enough to affect the motion. This usually occurs in gases moving at significant fractions of the speed of sound, or in systems where pressure and temperature changes are substantial. In incompressible flow, density is treated as nearly constant, and pressure mainly enforces motion. In compressible flow, pressure, density, temperature, and velocity are tightly linked through both mechanics and thermodynamics. The speed of sound is the speed at which small pressure disturbances travel through a medium. The Mach number compares the flow speed with this disturbance speed. When the Mach number is small, pressure information travels through the gas much faster than the flow itself, and the gas can often adjust in a way that resembles incompressible behavior. As the Mach number approaches 1, the motion of the gas and the motion of pressure information become comparable, and compressibility becomes central. Isentropic flow is the ideal reference case. Adiabatic, reversible, and without shocks or friction. In such a flow, changes in area can accelerate or decelerate a gas, depending on whether the flow is subsonic or supersonic. A converging passage accelerates subsonic flow toward sonic conditions. A diverging passage accelerates supersonic flow, but decelerates subsonic flow. This reversal is one of the defining surprises of compressible flow. Choking occurs when a limiting sonic condition is reached at a throat or in a duct. Once choking occurs, lowering the downstream pressure further cannot increase the mass flow rate in the same way it did before. Fanno flow isolates the effect of friction in an adiabatic, constant area duct. Friction always increases entropy and drives the flow toward a sonic limiting condition. Rayleigh flow isolates the effect of heat transfer in a frictionless constant area duct. Adding or removing heat changes temperature, density, pressure, and Mach number in coupled ways. Both models help explain flows in pipes and ducts, where friction or heat transfer are the dominant effects. Shock waves are the most dramatic non-isentropic feature in compressible flow. A normal shock is a very thin region in which a supersonic flow is abruptly compressed and turned into subsonic flow. Static pressure, temperature, density, and entropy rise, while stagnation pressure falls. The shock is not a reversible compression. It is an irreversible event with mechanical energy loss. Chapter 11 extends fluid mechanics into a regime where thermodynamics and wave propagation cannot be separated from motion. The familiar ideas of mass, momentum, and energy remain, but density is no longer a passive property. Chapter 12. Turbomachines, pumps, fans, compressors, and turbines. Turbomachines are devices that transfer energy between a rotating shaft and a fluid. Pumps, fans, blowers, and compressors add energy to a fluid. Turbines extract energy from a fluid and deliver shaft power. These machines appear in water supply systems, aircraft engines, power plants, HVAC systems, automobiles, ships, industrial processes, and many other applications. Their variety is enormous, but the central fluid mechanical idea is the same. Rotating blades change the angular momentum of the fluid. Angular momentum gives the deeper explanation. Fluid entering and leaving a rotor carries tangential motion relative to the axis. If the rotor changes the tangential component of the fluid velocity, a torque is required or produced. The shaft power is connected to this torque and rotational speed. A pump impeller typically gives the fluid angular momentum. A turbine runner typically removes it. Velocity triangles are the language used to describe the motion at rotor inlet and outlet, combining absolute velocity, blade velocity, and relative velocity into a coherent picture. The centrifugal pump is a major example. Fluid enters near the eye of the impeller and is flung outward through rotating passages. The impeller adds energy, and the casing helps convert part of the velocity into pressure. Pump performance is described by curves showing head, efficiency, and power as functions of flow rate at a given speed and impeller size. The actual operating point is determined by the intersection of the pump curve with the system curve, representing elevation change and losses in the piping system. Cavitation is a critical pump concern. If pressure near the pump inlet falls too low, vapor bubbles form and later collapse in higher pressure regions. This can damage surfaces, reduce performance, and create noise and vibration. Net positive suction head is a way of expressing whether the inlet conditions provide enough pressure margin above vapor pressure. Similarity laws allow turbomachines to be compared and scaled. Dimensionless parameters organize performance data and allow model tests to inform prototype design. Turbines come in impulse and reaction forms. In an impulse turbine, much of the pressure drop occurs in nozzles before the fluid strikes the moving buckets or blades, and the rotor extracts energy, mainly by changing the direction of high-speed jets. In a reaction turbine, pressure changes occur through the rotor passages as well as stationary passages, and the blades operate with both pressure and momentum changes. Chapter 12 brings the course together. It uses energy balances from Chapter 5, angular momentum from control volume analysis, similarity from Chapter 7, pipe system behavior from Chapter 8, cavitation awareness from Chapters 1 and 3, and compressible flow ideas from Chapter 11. Turbomachines are therefore not an isolated topic at the end of the book. They are a synthesis of the whole subject, showing how fluid mechanics becomes rotating machinery that moves water, propels aircraft, generates electricity, cools buildings, and powers modern industry. Of the 12 chapters we have just moved through, the one that perhaps plants the most seeds for what follows, is Chapter 7, Munson's treatment of dimensional analysis, similitude, and modeling. There, the Buckingham pi theorem was introduced as a formal method for reducing a many-variable problem into a smaller set of dimensionless groups. Reynolds number, Froude number, Mach number, Weber number, and Euler number each made an appearance, organized around the idea of matching force ratios between a model and its prototype. That treatment is exactly what an engineer needs to design a wind tunnel experiment or scale a pipe flow result from laboratory to plant. But Munson's Chapter 7, by necessity, stays within the boundaries of a single introductory course. It does not venture far into heat transfer, mass transfer, chemical reaction, particle dynamics, or the rheology of complex fluids. And those are precisely the territories where chemical engineers live. The chapter that follows picks up where Munson leaves off. It takes the same intellectual framework, physics expressed as competing force ratios, collapsed into dimensionless form, and extends it into the full working vocabulary of chemical engineering. Prandtl, Schmidt, Nusselt, Sherwood, Peclet, Damköhler, Stokes, Capillary, and several others besides. If Chapter 7 taught you what a dimensionless number is and why it exists, what follows is an attempt to show you how many of them you will actually need and what physical ratio each one represents in the flow.